Now we will introduce a very important concept called rotation factor. Suppose A is a complex number, and we discuss A times e to the power j psi. We represent A in the system of polar coordinates, that is, A equals its modulus times its phase angle. Suppose the phase angle of A is theta, it times e to the power of j psi. We can get the answer is the modulus of A times e to the power of j theta plus psi. Thus, we can find that any complex number times e to the power of j psi means that the modulus of the complex number is the same and the phase angle is ended counterclockwise by psi degrees. By using Euler's formula, now we will take psi with some special values for examples. First, psi equals a half pi. We can evolve it like this. As we know, cosine a half pi equals 0 and sine a half pi equals 1. So it equals j. After this, let's discuss that any complex number timing j equals it timing e to the power j a half pi. According to the discussion we made right now, we can easily know that any complex number timing j equals to it rotating counterclockwise by 90 degrees. That is this. In a similar way, we can evolve e to the power of minus j a half pi by using Euler's formula like this. Cosine minus 90 degrees equals 0. Sine minus 90 degrees equals minus 1. Thus the answer is minus j. Similarly, minus j times a equals a times e to the power of minus j times a half pi, which means a rotating counterclockwise by minus 90 degrees or a rotating clockwise by 90 degrees. The third special situation is that psi equals pi or minus pi, which means this. As we know, cosine pi or minus pi both equals minus 1 and sine pi or minus pi both equal 0. Thus, we know that the answer is minus 1. It means that any complex number timing minus 1 equals it timing e to the power of j timing pi or minus pi, which means it rotates clockwise or counterclockwise 180 degrees. It's the same as your instincts. In this discussion, we can find that j, minus j, and minus 1 are all rotation factors in the world of complex numbers. And next, we will discuss a very important concept. How can we use the complex numbers to represent the sinusoids? Let's take a complex function like this. Suppose at equals the square root of 2 times I times e to the power of j times omega t plus psi. We can expand it with Euler's formula as the square root of 2 times I times cosine omega t plus psi plus j times the square root of 2 times I times sine omega t plus psi. Can anybody see it? The sinusoid we discussed just now is the imaginary part of the complex function. Namely, the square root of 2 times I times sine omega t plus psi equals the imaginary part of the corresponding complex function. What's the importance? We can rewrite the complex function in detail like this. Be careful of the expression with the red line. It's a complex number, obviously. Furthermore, it represents both of the effective value and the initial angle of the sinusoid. Thus, we can use a complex number to represent a sinusoid by one-to-one mapping. We rewrite it as I with a point on the top. Similarly, for a voltage like this, we can find a complex number as U with a point on the top to represent it. The I point and U point are both phasors. At the beginning of the lecture, we introduced that a phasor is a vector with the information of phase. Attention here, it's a vector with a modulus and a phase angle, where the phase angle includes the phase information of corresponding sinusoid. That's being called a phasor. For convenience, we can rewrite it like this. Then we will give two examples. We need to change the time domain expression into the corresponding phasor expression. For this, its amplitude is 141.4 ampere, equivalenting the square root of 2 times 100. Its initial angle is 30 degrees, thus we can rewrite it like this. As for this, we are aware that it equals the square root of 2 times 220, and we need to know that the RMS voltage in China's home outlet is 220 watts. The initial phase angle is minus 90 degrees. Thus, its corresponding phasor is like this, and the units are volts and ampere, respectively. Let's see the second example. The modulus, initial phase angle, and the frequency are all known. We need to express it in the time domain. According to the mapping relationship, we can easily find that the current equals the square root of 2 times 50 times the sine 2 pi times 50t plus 15 degrees. The unit is ampere. Based on the one-to-one mapping relationship, we can easily map the time domain expression and the phasor expression of any sinusoid.